Sophie, you're muted.
Here's Anika, thank you. Well, yeah. Hi, everybody. Welcome to this week's MPlan Paper Club. My name's Sophie, and I'm here to go through Ying et al.'s 2001 NeurIPS conference paper, Do Transformers Really Perform Badly for Graph Representation? This conference paper was a collaborative effort from a number of organizations, including Dalian University of Technology, Princeton University, Peking University, and Microsoft Research Asia. And it went on to win first prize in the same year for a competition to use AI to predict quantum properties for more than 3.8 million molecules. In this paper, the authors introduced the Graphormer as a kind of a first deep learning model that's built upon the standard transformer, transformer, and it outperformed conventional kind of GNNs, sort of as graph sage and that sort of thing on particular use cases. I've chosen to look at this paper today because I was really interested to see how transformers are being used kind of for non-sequence type tasks. And so here we go. Here's just some general information about kind of the authors, the institutions, where you can find the model online. It's on Hugging Face. You can also find the code on GitHub, and you can get the paper from these two links. I also tried to look at it from the NeurIPS link because it was a NeurIPS conference paper, but unfortunately I couldn't find it there. The link seemed to be broken, so just flagging that there. I will make these slides available online in case everyone wants to follow up on these later and get this information from there. So what will I be covering today? So just to let you know how this kind of presentation is going to go, I'm going to look at the objectives from the paper, look at the outcomes from it and its legacy, so kind of look at that all together at the start, then go over some background concepts that are useful just to kind of understand some of the key innovations, which I'll go into next, then the architecture, and then look at the more detailed results from this paper. So starting with objectives. The main objective that I got out of this paper was that they wanted to explore whether the transformer architecture can be leveraged to learn graph representations. So I really wanted to flag this here because I know that transformers have become rather popular now, especially because they're a key element in Gen AI. That's particularly the decoder part of the architecture. Now, this is from 2001, so at the time, generative AI hadn't got quite so far. So here they're actually using the encoder part of the original kind of 2017 paper's architecture. So just thought that's kind of useful just from the beginning to get your mind on the right path that, think BERT, think encoder, transformer, rather than think, a kind of standard generative decoder architecture here. So just to get that done. So if we go back and say, okay, so the primary goal was to explore whether the transformer architecture can be leveraged to learn graph representations. And they set out kind of three key pass criteria to say whether it can or not. I've extracted that from the introduction. They have one, create a GNN which embodies the ideals of a transformer architecture, so something that can work with graphs and transformer architectures, that it can perform some graph representation tasks efficiently, and it also outperforms classic GNN models. One thing it seems very concerned about in the introduction is, looking at how transformers have really made such a big impact on the rest of the world of deep learning. It's used on images and things like that. And they were like, okay, so why is it not really taking off with graphs? Can it even be adapted to use for graphs? So here I have a very basic kind of idea, just to summarize kind of what the pass criteria is. They want to take a graph, the transformer architecture, and they want to do some graph representation tasks. So those kind of tasks can be, node classification, node regression, link prediction, link labeling, graph classification, and they want to do it the best. They want to do the best out of all of the different kind of architectures there. That would be kind of their goal, to see that it could be competitive with more classic traditional graph architectures or GNNs. But again, just so I don't lead anyone into too much confusion just from these images at the start, I just wanted to say, okay, this paper mainly focuses on graph level tasks. So, it really looks at graph classification and graph regression. It doesn't really look at node or link kind of level graph representation tasks. And as I said beforehand, when they're talking about the transformers that it's using, it's very much focusing on that encoder architecture. So yeah, I did include this as a stretch goal, and I did kind of get the vibe from the introduction to this paper that I've put in that the transformer model, they really wanted to see the transformer model variants for GNNs becoming more of a de facto standard for graph representation tasks, which they certainly weren't at the time. So so when we look at the outcomes, let's see how they went against these goals and pass criteria. So they passed all the 3 pass criteria. Yay, that's very exciting for them. They did create a GNN transformer that aligns strongly with the encoder architecture. It can perform graph representation tasks, and it did achieve state-of-the-art performance on some key graph representational tasks, outperforming more traditional like architectures like graph sage and things like that in this particular category. This was the award that they won in 2001, and they got first place looking at this particular task, which was a graph regression task to see how well the model could identify some of the quantum properties to do with molecules. And this, I believe, is something to do with the energy levels of the molecules. Unfortunately, I do not know enough about molecules and chemistry to give more than that, but I thought that that was quite exciting. However, transformer models do not become the de facto standard for graph representation tasks following this. This is due to some of the limitations that they even mention in the paper themselves. One of the key things that they're looking to do within the paper is actually to really have that kind of global attention that is possible in transformers. You're able to look at the whole sequence. They want to look at the whole graph and really get that whole graph information out when they're looking at the importance of the representation of a particular node. And this just leads to huge scaling issues. Large graphs, there's quadratic complexity that's introduced by this attention mechanism. So it really limits the size of the graph that this sort of architecture can be used for to keep it practical and even have the computing resources available for. There are some other considerations as well about why this didn't become kind of the de facto kind of standard. They do report incredibly positive results for graph level representation tasks, but they don't comment. The paper doesn't comment on node classification or link prediction, and I haven't read all of the papers, but I understand that they've never really been competitive against just kind of like traditional DNNs like GraphSage, GraphConv, and like GIT and things like that. GNNs is just simpler to implement and tune and train. There isn't as much hyperparameter tuning. You don't have to kind of get so involved. There's no lookup tables. So that's another reason that if you kind of want to just kind of get going with a task quite quickly, more traditional architectures also are preferable. Again, as I mentioned beforehand, Graphormers have a huge computational cost that comes from that kind of global attention that they introduce through this paper. And also that the domain that they're looking at in this paper is quite specific. They're looking at molecules which are in the scheme of what graphs can be, relatively small. They can be quite dense graphs. They can have quite meaningful edges, and not all graphs are necessarily like this. So, knowledge graphs, social networks, things like this might not kind of fit this particular use case. However, that doesn't mean that there's no point reading this paper. Actually, this paper led to the development of the Graphormer V2, which addresses some of the scaling limitations. It also set off a wave of kind of hybrid architectures that really do kind of use a lot of the elements of this paper. And it continues to remain one of the top models for graph level molecular property prediction. And it's the baseline when training many new kind of graph transformer or kind of hybrid architectures. This one's often very much used. So it did actually have a lasting impact, and it did alter the field. And for particular tasks, this kind of remains kind of one of the gold standards or gold standards architectures, 4 or 5 years later. Oh, and I always put in a fourth one of these. I also think it's this paper is just a neat and interesting look at how architectures from one task can be adapted and used in another task. I think that by itself is quite useful thing to look at. I will say that I found the paper sometimes quite hard to read, mainly because I think that being a conference paper, they condensed quite a lot of information into some quite tight sentences. So it did take me a bit of time to unpack. So if something that I say does seem a little bit off, please do shout. But I still think that I'm it's a very useful paper to kind of look at that kind of creative thinking and using that kind of cross-pollination of ideas. So that in itself is quite fun. So looking at some background concepts. Now, basically, I think these are just to go over things that I think it's really useful to kind of be aware of if you're thinking about some of the key concepts in this. So graph basics, graphs are made up of nodes and edges, vertices and links. And every node can link to any other node, but they don't have to. So there's no kind of like set order. Nodes and edges can both have features. So, you know, like a node might have a set of features and the edges might have a set of features themselves that kind of separate them out from other edges. That might be useful to learn during training. And graphs can be directed or undirected. So, you know, they can have a particular order. They can just go one way, but not necessarily. Or making these a little bit, yeah. So it's an interesting kind of structure that the graphs have. And examples of things that you would like come across as graphs is, you know, social networks can be represented in a graph. Knowledge graphs are quite popular, but even road networks can be considered kind of a graph, or, and as we said before, kind of molecular structures. So these do kind of crop up a lot. One of the interesting things about them is they're often described as not fitting neatly in Euclidean space, as so neatly as some of the things like a sequence might, and often they have to be embedded in order to like work with a Euclidean space. So that's one of the interesting things, that graphs are inherently more complex to deal with than when dealing with sequences, but I'll have more on that later. So here's some very basic graph notation that I have extracted from the paper. So basically, this is just, you know, just in case you haven't worked with graphs before. So, you know, graphs can be expressed as G for graph, as like a function of its vertices and its edges. So where V is all of the nodes, E is all the edges, and VI is an individual node, or XI is an individual node feature. Some of the key elements of kind of GNNs that will be similar across most of them is that they're comprised of, I should take a step back actually. So I think a basic understanding of GNNs is really useful when looking at this paper, is that they actually are explained in the paper as well. So some of the key elements of GNNs are message passing. So each node aggregates information from its neighbors. This means that it tends to only get information from the nodes that it is connected to. So if it's not connected to a node, it will not get information from it. And there is an update function where that aggregated information the node gets from all of its neighbors is combined with the node features and updated as the layers go along. By this sharing of kind of, so, you know, as it happens, so the first time this happens, a node might learn a little bit about its neighbors. And for the second layer, for like a GNN, it's able to know a little bit more about what's going on in the graph, because its neighbors have now got information about its neighbors, and therefore it's able to kind of spread its knowledge about what's going on in a graph. So that's how some of the key ways that GNNs are trained. There's an optional kind of step for GNNs. This is the readout or kind of pooling stage. This is when all of the node embeddings can be aggregated into a single vector. And this vector is then used for graph level tasks. So this is something that is used in the Graphormer, which is looking at graph level tasks, but isn't necessarily something that you'll see in all GNNs. There is, however, usually a task level head, and that is what can actually say, so what is actually being, you know, applies the final layers to actually be specific for the task, whether that's classification, regression, or the like. So here, if you want to take the bits from the paper, is where you can see that these functions will fit in here with the aggregate function here and combined and readout. And also an example of a task level head might be like a linear and a softmax for classification. Yeah, so the inputs to a GNN will tend to be the embedded node features, the node index, so the graph knows which nodes to, you know, are neighbors, and can actually build an adjacency matrix in order to be able to aggregate the information, and also potentially edge features, which I think are used in some GNNs. I haven't used it that much, but they definitely are used in Graphormers, and I would be surprised if they're not used in other architectures. And of course, the outputs, which would be depending on the task level head. So those are some of the key things to kind of keep in mind about, like, you know, the GNN features. Transformers, I know that they've been very big over the last kind of like 5 years, so I'm not going to go into too much information in this talk about them, especially as that kind of background knowledge. But did want to draw attention to kind of like these key elements of transformers. So, when we think of a transformer, the input embeddings are a key part that we think of. They were developed to work on sequences. And actually, I think from the 2017 paper worked on, was originally designed for like a neural machine translation. So actually, a sequence to sequence kind of like ideal. So they're like very much designed to look at a sequence. And the big innovation that the 2017 paper had was that, of course, that it could use attention to look at the whole sequence and use all of that information when it's translating it to the new one. And of course, the input embeddings are the key point for transforming words, the words that were in the sequence, into tokens and using those. So that's a key part of it. The positional encoding is also a key part of like a transformer architecture, looking at because that is really key for the model to be able to learn the relationships between the words, even if they're not in like the exactly next to each other or in a different order within the sentence. Also within a sequence, the positioning is like fundamentally important to understanding what the sequence actually means, well, especially for a sentence, even though I'm trying to jumble that with my English at the moment. But so that's another thing that's really important for the positional encoding, is actually getting that kind of set structure, which is quite important for transformers as well. Self-attention mechanism is a key part of transformers, which I'll describe a little bit more on the next page, but I am sure people are well aware of self-attention, and also the stacked transformer layers and the output layer. So the key 3 ones of these that are particularly important for this paper are the positional coding, as I've kind of mentioned, which is an encoding that injects positional information into the embeddings, helping the model to learn the relationships between the tokens, or in this case, nodes, based on the order, distance, or structure. Self-attention mechanism, the mechanism that allows each token within a sentence or node within a graph, in this case, to look at all of the others to decide which is the most relevant to its representation. Often this would be said it might be called its meaning if we're looking at a sentence, but I think meaning and node didn't really work that well in my mind. So I think it really is about like which is most relevant to the representation and to extracting the information for the particular task that's being trained on. And the stacked transformer layers. And the stacked transformer layers are a key to the transformer. Not only did they unlock the parallelization of these models to allow them to really like scale up to these giant sizes and to be able to be trained in like a reasonable duration, but also the get to someone really cool. But also these layers kind of allow the model to like progressively refine each token or node's representation and capture increasingly complex relationships about the input. So that's kind of a little bit of transformers and the key things that are good to know about that for this paper. So what are the key innovations? So the key innovations in this paper are the method of capturing graph structural information within the model, and also the way that they apply truly global attention, considering all nodes, to a graph task. So here, the 3 structural solutions that they add are centrality encoding. They alter the input features by incorporating degree centrality information within them. They add spatial encoding, which adds a spatial bias to the attention mechanism. And they add edge feature encoding, so it adds a bias to the attention mechanism to capture edge feature information. Now, we'll go into these in a little bit more detail in kind of the architecture section, and actually have some extracts from the paper, so we can kind of like go through that together. Arvid, please.
Yeah. One quick question: the edge features here, they are categorical, right? They're not continuous, yes, like edge weights also.
Yes, my understanding is that they're categorical. So it might be, I'm trying to think of an example of like an edge. Like it might be like the particular like bonds between like a categorical bond in a molecule that might be like different between different things. I know that we use graphs a lot at work, and we might have like a different way that they join, like, join to a task based on one of the features. So something like that, yes.
We have as say players in a football match, whether they're on the same team or not. But we also have continuous variations, like what's their angle relative to the goal, for example. So they can be both, right? But it's I think this one particularly excludes the continuous version.
That was my understanding when I read it, completely. But that is a really good thing to note. But yes.
Thank you.
So yeah, and so yeah, the edge feature encoding, and at this point, and I think I will add that to the notes before I put them online, that this is kind of it's categorical. So again, looking at the so yeah, that was looking at kind of like the structural kind of solutions that they put in. But looking at the innovations that they really did in this paper, the transformer architecture, as I've said, was originally designed for sequence modeling, where the elements have like a natural ordering that can be encoded intuitively with less positional information. So one of the things that this paper really looked at was how to incorporate this structural information into graphs when it's originally designed for sequences. So here's just a list of some of the kind of key differences between sequences and graphs. A lot of this I've kind of covered already, but it's kind of good to have listed here for reference. So you know that the sequences have a linear order, while graphs do not have a linear order, and they can be connected in arbitrary ways. A sequence would usually, a token will usually have a maximum of kind of like two neighbors, but in graphs they can have a flexible number. They can be all by themselves, or they could be connected to every other node. And this is what's captured in the centrality encoding that they include in the graph. There's a fixed way that you're meant to read a sentence, to capture its meaning. As with graphs, there are such things as topological graphs and the like, but there can be multiple ways to read a graph and multiple start points and things like that. So that also adds a level of complexity and difference. And again, like the being able to tell the difference between the distances within a graph could be significantly different to a sequence. As a sequence, it's quite easy to say that's one step away or that's 2 steps away, but with graphs, it's not always as easy. That said, the shortest distance is kind of the industry standard for kind of telling the difference between like nodes in a graph. So how many steps or how many nodes do I have to go through to get to this other node? Is usually the method that's used to tell the difference. So yeah, just at a high level. So how can we kind of summarize that? As a sequence, it's like a line, and a graph is like a web. There's a basic kind of differentiation between the two. This paper wasn't the first thing to actually look at including, trying to incorporate the transformer structure along with graphs. So there, I've just included 2 different examples here that are kind of from around the same time, so kind of like the year before. So I actually think the GraphBERT's 2020. So the graph transformer, that actually used a different way of doing spatial encodings. It looked at using the spectral sphere, so looking at using Laplacian eigenvectors to encode the positional encoding of the nodes. So similar to the 2017 paper, the way that I think that's in the 2017 paper, but at least the way that a lot of positional encoding is done now for transformers, this positional information is added straight at the beginning in the input, and is actually so yeah, it's kind of like added, and it does have like a learnable function alongside it. So it's using the eigenvectors, but the importance of the different positions can be learned, but that's added kind of right at the start at the input at this level in that graph transformer paper. For GraphBERT, it also used the Laplacian eigenvectors at input, but it also added this relative positional encoding between nodes, leveraging the shortest path matrix. So this was able to kind of also get that shortest path information into the architecture, and this this was added to the model actually in the attention network as a bias. So that's kind of how these kind of prior solutions looked at doing this. So the innovation, so that's can see how, we have the spatial kind of the differences coming through, how they've been applied and kind of how they're different. So the second innovation is really that global graph attention. So for each attention calculation, the Graphormer includes every node, even the ones it's not connected to, resulting in truly global attention. And again, when we look at the architecture, we can go a little bit more into how this works, but that is kind of one of the really big differences of the Graphormer paper. This in itself is not the first paper that actually did look at including some form of attention. So of course, I think in like 2018, they had I think it's 2019, but around that time, we have the graph attention transformer. And again, like and Bert was using the graph Bert was using attention and things like that. The difference is that these were always local, applied primarily to neighbors. Because as we said beforehand, with graphs, you really need that edge to combine the features. And it just and so any nodes that were not connected to any nodes in a graph that were not connected to the node of interest at the time, that information was not kind of included. And in some examples, in fact, the attention was limited to just being immediate neighbors as well. So again, that's kind of one of the really big differences in kind of what happens in this paper. So the architecture. So the key elements of the architecture is the inputs, which are embedded node features, edge indices, and edge features. Edge features being like one of the key things that this paper thought was really important to be able to include and to capture that information. There's a learnable centrality augmentation to node features. So kind of at that point of like we were describing for the Laplacian positional encodings. At the same point for this architecture, they actually add this kind of centrality augmentation to the node features kind of right at the start. This centrality augmentation looks at how key and how important a particular node is to the graph, and they'll look in degree and out degree. But again, we can go into that a bit later. But this is part of the architecture that's key. They also use a stacked encoder transformer architecture. So one node per layer, I'm not sure if that's what I wanted to have, but they have a modified attention to include spatial and edge features. So it's very similar to the stacked encoder transformer architecture that you'd be familiar with. Which has the multi-headed attention and feed-forward layers and a layer normalization. Except in this case, the layer normalization is actually applied at the start before the features go through to having their having their attention mechanism applied. This differs from the 2017 paper, but in 2001, it was pretty much ubiquitous at the time. How does the positional encoding work for graphs? Sorry, I'm just taking a bit of time to looks like there's actually quite, yeah, okay. How does the positional encoding work for graphs? They're not supposed to have any order, so wouldn't have to lose this property when you start adding positional encoding. So for the Laplacian, I think that they deal with that by looking at kind of the eigenvectors. I'm not quite sure how that works because I don't do that in this paper, so I didn't look at that in too much detail. But what they do is they keep it, my understanding is they keep it relative. So they look at, so these centrality augmentation that they do here, that's not positional per se. That's looking at how many connections does in and out connections does this particular node have, and that's what they encode kind of at the level here. But what they do for when they're looking at trying to add that, they don't really call it positional, they call it spatial. And so when they're adding that kind of spatial element, they add it in at the attention mechanism layer, and it's looking at it kind of relative to other the shortest path to all of the other nodes in the graph. So I guess they don't really, that's how they get around the positional. They don't actually have it called positional per se. And for the Laplacian, I'm not actually quite sure, but I would definitely be keen to know a bit more. So there's a stacked encoder transformer architecture with this modified attention to include spatial edge features, and the layer normalization applied earlier, which was ubiquitous at the time, just because that by doing the normalization prior to calculating the attention, it was it just led to better training. There was less gradients exploding and imploding and things like that, because it was stabler. So instead of like normalizing across batches, it was normalizing across the layers. And then there's the mean pooling readout layer at the end. So that's the basic components of this. Where does each node aggregate get its information from? Do you mean like the features that the features that the nodes are using? All right, I will hopefully. So each node aggregate gets its information from. It gets its information from its. It gets its information in this one from actually all other nodes. Let's have a look at how this looks. So hold on, Arvid, please.
Sorry, I'm also a bit confused, right? So if I understand correctly, we turn the graph into a sequence first. Right?
No, the graph isn't turned into a sequence. The graph remains as a graph.
Ah, okay.
So, oh yes, that's a key kind of point. So, and the graph. So the inputs are a number of like node embeddings, which have the features for each of the nodes. So if you consider like it might be like the name or something, or the color or something, or something like that, will have a number of features. And they will be passed to the graph, but they don't get given any positional encoding at all. What will be encoded is the, so for that particular node, it will have structural information about that node encoded with it, not any sequential.
Okay, so yeah, probably very, very confusing. So why did they talk about this graph to sequence and encoding?
Which graph to sequence encoding? Apologies,
Am I on the wrong paper? But it's
I think we actually are on the, and I think I might be on the wrong paper. The paper that I'm presenting is
it's not the graph to generative pre-trained transformer.
No, I'm actually presenting the G transformers really perform badly for graph representation.
Okay, then my apologies, I messed them up.
That would be the case of the confusion. I'm so sorry. That's it for the confusion, guys. But yeah, I'm presenting the 2001 paper on graph transformers. Well, actually not graph transformers, but yeah, do transformers really perform badly for graph representation?
Okay, never mind then. Thank you.
But yeah, so yeah, no graph gets turned into a sequence in this paper. And again, the main and that's one of the main points of this paper, is that they kind of look at the graphs and use these structural encodings versus to kind of capture this information. So where were we? So with the mean pooling readout layer. So here's the diagram from the paper, which looks at the stacked encoder head. So as you can see, it looks quite similar to a encoder, like a encoder transformer stack. So here you have kind of the inputs of kind of the key and the query and the value that are informed by the node features, which are augmented by this centrality encoding that I was mentioning before. So these, so they have the node features, which are augmented by this centrality encoding, which has an augmented parameter, which is learnable. So you can see it can learn about so it can learn about what the centrality encoding kind of means while you're training it. So these node features and the centrality encoding pass through the attention mechanism, and they are combined with a bias of an edge encoding and a spatial encoding before being passed out and passed to the next layer, or ultimately to the readout layer in this paper. So the key, as I said beforehand, so these are the key parts of the architecture. So starting on the centrality encoding, this is what I've mentioned beforehand. So one of the key reasons to include the centrality encoding is that it can measure how important a node is in a graph, which is usually a very strong signal for graph understanding. So in the Graphormer, they use this degree centrality, which is yeah, I'm so sorry, Nico. I think yeah, I think there was some confusion on my part as well. I think I said I was doing the paper that I tagged earlier, and I wasn't explicit. So apologies for the confusion, guys, for the wrong paper. I hope you're enjoying this paper so far, and I will continue through it. And again, yeah, be more on top of that next time. Yeah, so the yeah, in the Graphormer, they use yeah, the centrality encoding, which assigns each node like 2 real valued embedding vectors according to its in degree and out degree, to be able to capture, how many edges, how many nodes are coming into this particular node, how many are going out, is it a bottleneck, how important is it, and really being able to augment the input by this by that trainable, I think this is this Z, I believe, is a trainable parameter, allows the model to kind of really understand how important this particular encoding is. As for the modified spatial encoding, this is the bit which it's kind of looking at how graphs can really capture that kind of version of positional encoding. So it's looking at structural encoding and spatial encoding rather than looking at that kind of traditional kind of like positional encoding. Because as you're very right to say, that doesn't really work for graphs. So that can't really be what's happening at this point. So this is where they use that the shortest distance. So that's using the number of hops. So is it like 1 hop, 2 hops, 3 hops between different nodes? Because what this modified attention does is it looks at every single node in the graph at the attention time. So it compares the features, or aggregates and combines and updates, or aggregates all of the features of all of the other nodes in the graph before it does its update. And so this includes, and this is the really exciting bit, is this includes nodes that it's not connected to. So nodes that it's, so as you can imagine, a hop might be, so it's always going to be like an integer value for the distance. So it's either kind of like 1 hop, 2 hops, 3 hops, and until you get to the furthest node from it. And if a node isn't connected at all, it's given the value of -1. And this is one of the really big breakthroughs in this paper, because it was able to actually have this kind of -1 to capture the information about nodes which are not actually neighbor or connected to an individual node to better get that information. So they include this as a bias, where this is the when a graph, we consider a function, this function here. There we are. That can get the which is kind of this function here. This I think is that theta, is that kind of like the shortest distance between the 2 nodes. This is then used as a lookup to fetch information via this V here, which is a learnable scalar vector. So it's a learnable scalar vector indexed by whatever this number of steps would be. So that would either be 1, 2, 3, or -1 if it's not connected at all. This does mean that that it doesn't allow for variation in like what the model learns is standard. It will say, okay, so if this neighbor is 3 times away, this is the bias that we'll apply, and that will always be the case. Or if this node is not connected, this is the bias we'll apply. That will, from what I understood, that would be static, but it does allow it to kind of learn that like over time, and get that information in there. So that's one of the big breakpoints of this this paper. And then the last bit, the edge feature encoding, which is also, yeah, this bias is added to the attention here. So it's able to be to capture that, and it's able to be able to learn in the attention how big a weight, how big a importance should you put on things that are at a different kind of like level of distance away from the node in question. For the edge feature encoding, this is also applied to the attention layer. So the attention mechanism, and it is able to encode the features of the edges in to the attention layer, so it can actually learn, given what the feature is, what the edge feature is, how important is it to kind of consider in understanding the relevance or importance of like this node and this link that is there. So those are the three kind of major like innovations that, well, not innovations, but the combination of these three elements are what really made this Graphormer particularly powerful. So look at the what are the results that we get? So these are taken from the paper. So here we have their first table, which is the results on this PCQM4M-LSC dataset. This is a molecular quantum property prediction dataset. So this is the one that's actually used in the, hold on, let me just move this down a bit. Used in the Open Graph Benchmark Large-Scale Challenge that they won. In this particular dataset, there are 3.8 million molecules. It's a very large dataset, and they were able to train their task to do regression here. So these are the models that it compares itself to, and kind of the main contenders at the time for this particular data set. So we have, graph convolutional networks, we have graph isotopic networks. Here they also train, this is the graph transformer, which I mentioned beforehand, which uses the Laplacian encoding Laplacian eigenvectors to create like a d-dimensional vector, which can be used to do the encodings. So yeah, this is the graph transformer, which is what it was using beforehand. Interestingly, because they wanted to be fair to the graph transformer, they actually increased the number of parameters that it had to retrain it. So like, oh, it doesn't have many parameters, it's probably not going to do that good on this task. Let's actually like beef them up again and see how it compares. So they actually do that, which I thought was an interesting, kind of a nice move on the part of the authors. So, but you can see that their model still beats it, even though it has about half the number of parameters, still performs better. And again, I'm just like referencing, this is the table of results that relates to this award that they won. Oh, this is a good thing to note, actually. So in order to get to this value, they actually, this value here that they use is the test MAE here, which differs from what's in the paper. They actually combine it with FLAG, which is a graph-specific data augmentation technique, which basically introduces a little bit of noise into the, actually, no, they don't do that for this one. No, this one that they just use for this one, they just use an ensemble. Forgive me, I got confused. But this one, they actually use an ensemble of different, they run an ensemble of the Graphormer a number of times, and then they average it and, take the average. And that's how they have this test MAE, which is a little bit different from kind of what we see in here. So that's the main difference for why that might look a bit different. So here are the other results that are like, that are given. So we also have the results on the a drug discovery data set, which has 128 labels as a classification task. They have a binary classification task, which is which is like a molecular biology kind of task as well. It's focused on identifying something to do with the molecules, whether they I can't remember what, but it's something to do with HIV. And here's the third one, which is looking at another kind of regression task for these kind of standard graph representation data sets. And these two here, table 2 and table 3, are additional Open Graph benchmark data sets. Now, these data sets tend to recommend that you fine-tune a model before you run it. So with these two, they actually used the model that they had trained for table 1. They used that model that was trained on that relevant data set, and they used that as their foundation model before fine-tuning on the training set for these data sets. And that's why they're kind of got this fine-tune. Well, it's good to know that these are fine-tuned, and where relevant, they've also done the same to their competitors to try and even the playing field on that. Here's where the flag comes in. So this is where they used the graph augmentation technique, where they add a little bit of noise into the into the graphs at training. They introduced this because as you can see, the size of these data sets are significantly smaller than the like 3.8 million size data set that they had won the competition on. And so by using this technique for these results shown in table 2 and table 3, they were able to actually overcome the overfitting problem that they were having and be able to have better results. But they did need to add this kind of extra augmentation into their model during training to be able to achieve that. It wasn't just kind of straight off the bat. As for table 4, this isn't an open graph benchmark data set, so they didn't do fine tuning on this, I don't believe. But again, this is for a very small number of molecules as well. I mean, a small data set. So for this one, they actually used just a smaller version of their Graphormer. So that's why it's called Graphormer Slim. It has a significantly fewer parameters. So that's one of the reasons it performed better on this particular data set. And that brings us to the, oh wait, we have the ablation study. Of course. So the other thing that they looked at was to see about, what are the key elements that we've introduced that are important, like what works, what doesn't work. So one of the first things that they do, of course, being very competitive, is they say, okay, what's the best way to kind of encode the node relationships? And they use that Laplacian kind of positional encoding that I was referring to as a comparison. And they say, okay, you know what, we've done, about we've done better than that. So let's just ignore the Laplacian PE and let's keep with the spatial, because this results say that they're better. I don't know how many times they ran these or whether they averaged them, but this is what the results show for why they selected that. And as you can also see that they looked at different ways of encoding the edge. I'm assuming this is the edge label, kind of via the node, via aggregation, or via the attention bias. And given the attention bias is what they've described in the paper, and also kind of what's performed best, this is where they've decided to include it. So the ablation study basically shows the increase in, or the decrease in MAE as the, as we add these extra features in for the model. And that's just an extra slide to point out that this is for the edge label encoding, because I found that was a little bit confusing. And so that brings me to the end of the presentation. Are there any questions? Well, I hope you enjoyed the paper. I am so sorry for the confusion, and I hope at least that was a comparison piece to the paper that you did read. And I'll be really interested to hear about that one. And I even tended to look at that one in particular, just to kind of give the comparison to this one, and to apologies for that, and thank you for coming.
Thank you very much. Great presentation.
There's a question.
Oh, sorry, I didn't see it. Yeah. Yes, my understanding is that the whole graph was the input to the transformer at once. And again, these molecules are not very big in the scheme of how big graphs can get. I think for and that's why I think that they don't really highlight that within the paper itself. That is a problem, though, that it can't actually deal with large graphs, which is dealt with to some extent in the Graphormer V2. I believe, but yeah, so I understand they pass the whole graph, and they would need to for the attention, right? They would need to get the attention layer to be able to get all of the nodes relationships. So yeah.
Cool. Thank you, Sophie. I think there's no more questions, comments, and yeah, again, I apologize for being confused from our part. We'll make sure it won't happen again. Yeah, we will see you guys again in 2 weeks. Yeah, have a nice day, everyone.
Right. Thanks. Bye, guys.
Thanks a lot. Bye.
Thank you very much. Bye.